Hi guys, so today we will be looking into the MobileNet SSD architecture and uh, we will be knowing the implementation of MobileNet SSD. So below is the simple, it's a one-layer architecture which involves the depth-wise convolution and point-wise convolution. So MobileNet SSD is built on two principles. One is the depth-wise convolution and point-wise convolution. And that is the reason why MobileNet SSD is faster as compared to our normal convolutional neural networks. Okay. So while moving forward, we'll be looking into why MobileNet SSD is faster, but the primarily root cause is because of the separation of our normal convolution to two convolution. One is depth-wise, and the second is point-wise. Now let's move forward to the next slide, where we are seeing that when we talk about a normal convolution, okay, this is our input image, and this is a filter, and this is the output we receive. So, for example, we have a filter of 1, 2, 3, 4, 5 channels. We will get this as an output, okay, for that layer. It's a normal convolution layer. Now, when we talk about a depth-wise separable convolution, okay, which involves a depth-wise as well as a point-wise convolution, okay. So this is the general process. This is the input image. We first do the depth-wise convolution, then do the point-wise, and then get the same output. So here also we are having 5 channels with a single channel having a dimension of 4 by 4. Here also we are having a 4 by 4 as an input channel, and we are having 5 channels inside it. Now, depth-wise separable convolution that is generally used in MobileNet SSD is faster as compared to the normal convolution. Okay, and this we will be looking in soon, like why it is faster. But the primary reason of this being faster is because it separates a normal convolution into two parts. One is a depth-wise convolution and another is a point-wise convolution. Okay, so let's move forward and check basic understanding of why it is faster, right? So here you can see, let's first compute the computational cost of a normal convolution, right? So here you have a 6 by 6 by 3 as an input image. You apply a filter of 3 by 3 by 3 and you get a 4 by 4 channel. Okay. Now let's assume you use 5 filters. Okay. So the number of channels in your output is 5, right? Now when we compute the computational cost, we will multiply the filter parameters, that is 3 by 3 by 3, into the filter position, how many positions they will, you can say, move in this particular input channel. So because we are getting a 4 by 4 output, so it means that that many number of times my filter moves, right? And how many filters are there? There are 5 filters. So my complexity will be 2160. So this would be my computational cost, right? Now, this is for my normal convolution. Let's move forward to our mobile net convolution. Okay. So here you can see in a mobile net convolution, we have two convolution, right? One is the depth-wise and another is the point-wise. Let's first calculate for the depth-wise. Okay. Now, before moving to the depth-wise computation, let's first see how MobileNet works. So this is, let's say, your input image, then it applies a depth-wise convolution, then a point-wise, and it does this 13 times in a loop, okay? And then it provides the output, right? So let's move forward. So 13 times, I mean to say, this process is generally happens 30 times. A depth-wise and a point-wise is one, and then this happens 13 times. That is the complete architecture of MobileNet that we'll be looking soon, right? Now let's first look at the depth-wise convolution. In depth-wise convolution, this is your input image. You will use a 3 by 3 filter, okay, and then you get some output, right? So once you multiply a 3 by 3 filter with an individual input, right, you will get a channel here. right? So now you are getting output as 4 by 4 by 3 because you use three filters here, right? So because you are using three filters, you get three channels here, right? And for individual filters, you will be getting a single channel, right? Now let's move forward and calculate the computational cost. Now because you are using a 3 by 3 filter and number of times the position is changing is 4 by 4 and the number of filters are 3, so you get a calculation of 432. Now remember one thing here, which is very important, right? Here your computational cost is 432 in your depth-wise convolution, right? Previously, in a normal convolution, you are having 2160. That is because you are considering a 3 by 3 by 3 filter. Now here, instead of using a 3 by 3 filter, a depth filter, you are just taking a 3 by 3 filter and multiplying by the individual values. Okay, so I hope I'm clear on this part that here three filters means a 3 by 3 dimensional filter, and you are applying individual multiplication of this filter with individual channel. Okay, so on three channels, you multiply a 3 by 3, and then you get a 4 by 4 by 3, right? Now, to get a understanding of feature importance in the depth, we do a pointwise convolution. Now, in the pointwise convolution, this is the output you receive from a depthwise convolution. You multiply the filters of 1 by 1 by 3. That will be five filters that you will be using. Okay. And then you are multiplying the depth, individual depth of it. Okay. So your 4 by 4 by 4 input, once multiplied by 1 by 1 by 3, will get you a single channel. And because you are getting using five filters, so there will be five channels as your output. Now you can see you will get a 4 by 4 by 5 output similar to the way you are getting in a normal convolution as well. Here you also having a 4 by 4 single channel dimension with five channels, right? Now moving forward, let me just update this thing. Maybe it seems a little confusing to you guys. So let me update this particular part here. Instead, so I hope now it's much clear, right? So these 3 by 3, right? These are multiplied by your single 6 by 6, which will give you a 4 by 4 here, right? Now again, these 3 by 3 will be multiplied to the second channel and like so on. Okay. So let's move forward to this and let's go to the computational cost of your point y. So similar to previous one, we'll be taking the filter params, which is 1 by 1 by 3. The number of filter positions will be 4 by 4. I multiply by the number of filters. Here we are using 5 and we multiply it by 420 to 240, right? So for the pointwise convolution, the number of uh, the computational that you are getting is 240. And to get the complete computation of MobileNet, we just simply add that and we will get 672 as an output, right? So if we compare the computation cost that we get in MobileNet SSD and as compared to a normal convolution, we can see that there is a 30 times 0.31 ratio, which is 30 times more efficient than your normal convolution, right? Because we separate the the complete normal convolution into two parts. One is the pointwise, and the second is one is the depthwise, and second is the pointwise, right? And in general, we see when we implemented this thing in general, we saw a 10 times efficiency, right? Instead of 30 times, it's theoretically getting we are getting a 30 times efficiency, but in general, when we implemented an on real life scenario, we are getting a 10 times more efficiency, right? So I hope this thing is clear to you. Now let's move forward with this. The important part is you remember that in depth-wise separable convolution, you are having a depth-wise computation and a point-wise. Okay, so this particular computation is divided into two parts. One is the depth-wise and another is the point, right? So let's move forward to the original architecture of MobileNet SSD and we'll be understanding how it works, right? It's very simple if you guys are able to understand the depth-wise and the point-wise convolution. Okay, now see here. in the paper itself, they mentioned that on the first layer, they are doing a convolution on the input size of 224 by 224 image of depth 3 and having a filter of 3 by 3 by 3 by 32 channels. Okay, so it's a normal convolution that they apply. So from this particular input, you get this as an output, right? So here you can see the number of channel will be 32 in the output, right? So for the next particular layer, this would be your input. From the filters, you get 32, and then once you multiply these filter shapes, so it's a normal convolution, right? You will get 112 by 112. Now you apply a depth-wise convolution to it. Okay. Now with the stride of one. Now look at this carefully. When you do a depth-wise convolution with a stride of one, you get the same channel as 32. This is what we discussed, right? The channel remains the same here, right? And when we do the pointwise convolution, the channel will increase. So in the third layer, in this particular thing, the third step, what we are doing a pointwise convolution. So here the size would be the number of channels multiplied 1 by 32, multiply the number of filters we want, that is 64, right? So in the next input, we will be having a 64 input, right? And the size remains the same, but the depth increases. Then again, we are doing a depth-wise convolution, right? But here now we are using a stride of 2, and that is the reason our depth remains 64, but our input dimension, or you can say the channel dimension, reduces to 56. And this keeps on repeating itself. Okay, so here you can see they mention this as well. This is the first particular depth-wise separable, which involves a depth-wise convolution and a point-wise convolution, right? So when we move forward to this, we will be doing this 14 times. Okay, if we include this, then we'll be doing it 14, otherwise we'll be doing it for 13 times, right? Now, after doing this as 30 times, as we discussed previously, that this particular thing of a depth-wise convolution repeats 13 times, and then we get a flattened layer. And after that, we process our input image to get the prediction, right? So I hope you get a brief understanding of how MobileNet SSD work. And thank you for joining. Uh, Looking forward to see you in the next video. Thank you.